And good afternoon, everyone. My name is Maximilian Weitzer. I'm a PhD candidate at the Chair of Energy Process Engineering at the University of Erlangen-Nürnberg. And I would like to show you the project I'm working on called SolBioRef, where we develop a pellet boiler for micro-CHP, combined heat and power, with an organic Rankine cycle. I would like to start with the objectives of this EU project, SolBioRef, then move on to our pellet boiler concept for micro-CHP, and show you our test results that we had with primary measures at this boiler, and in the end give you a summary and outlook. So what is the motivation behind this project? We have on the one hand, combined heat and power with biomass is still considered to have a large unused potential, especially in the small scale. And on the other hand, we have this well-established technology, organic Rankine cycles, that can generate power from low temperature heat sources, also especially in the small and medium scale. And we would like to combine these two to make a micro combined heat and power with a biomass boiler and an organic Rankine cycle. So the challenges in that project are to reduce the specific investment costs, increase the cogeneration efficiency, and of course also reduce the emissions. So that in the end we have a flexible, efficient, small-scale unit for combined heat and power, and with that contribute to the reduction of emissions and to the decentralization of energy systems. The EU project SolBioRef, it's quite a big project with 15 partners from universities and industry from all over Europe. And to put it in one phrase, you could say that SolBioRef will develop an innovative renewable energy system based on a novel heat pump-based configuration that produces heating, cooling, and electricity for buildings. But what that means is better explained at this slide, where you can see the flow scheme of the SolBioRef system. And SolBioRef stands for Solar, Biomass, and Reversible System. So solar biomass, these are the energy sources for it. And the core of this whole system is this reversible organic Rankine cycle heat pump configuration, where you can have, on the one hand, operate it as an organic Rankine cycle to produce electricity from heat, or you can also operate it the other way around as a heat pump and take low temperature heat and lift it to a higher temperature level with electricity. That's the core of the system, this reversible heat pump ORC configuration. And it's also covered with an adsorption chiller. So with this configuration, you can produce heating, cooling, and electricity with one single machine. So the expander in ORC mode works as compressor in heat pump mode. And additionally, you have on the rooftop these vacuum tube solar collectors. They collect the solar heat, bring it to this buffer tank, to the storage tank. And there it gets interesting for us in the bottom side. When there is no solar heat, we have this biomass boiler that is coupled with the ORC for combined heat and power. So as I just said, we have two modes, the summer mode, where the energy comes primarily from solar heat, and the priority is on space cooling. And when we have enough space cooling, the excess heat can be used for electricity production in the ORC mode. Or the second case, the colder or winter mode, where we don't have enough solar heat and we produce heat with our biomass boiler. There the priority is on heating, and excess heat from biomass boiler can be used for power generation in the ORC. So our main task in that is the development of this pellet boiler, where we do, on the one hand, include some primary measures like exhaust gas recirculation. So we take a part of the flue gas, of the exhaust gas, and bring it back to the combustion zone. And like that, we reduce the temperatures at the grate, we avoid hotspots and ash melting, and reduce the emissions. And additionally, we can operate the boiler with a lower air-to-fuel ratio and get higher efficiencies of the boiler. And the second step that we are currently working on is the internal heat exchanger in the combustion zone, So normally, that's a typical problem of these systems. Pellet boilers operate at maybe 80, maybe 90 degrees Celsius, which is sufficient for heating, but for operating an ORC, it's quite low, these temperatures, to get good efficiencies of the ORC. So we include this internal heat exchanger in the combustion chamber in order to supply the ORC with high temperature heat of more than 100 degrees Celsius to get better efficiencies of the organic Rankine cycle. So the key advantages of this setup are the high cogeneration efficiency, the increased electrical output of the ORC, and of course, due to the exhaust gas recirculation and other primary measures, the reduced boiler emissions. So here you can see the setup, our current setup in our laboratories. It's basically this pellet boiler from the Austrian company Ökofen, and on the right side you can see some gas analyzers for gaseous and particulate emissions. Our methodology, so what do we do step by step? We started with some tests with the unmodified standard pellet boiler from Ökofen to have some reference values of the emissions. Then we did a stepwise retrofitting of the primary measures. So we first included an exhaust gas recirculation where we bring some of the flue gas back to the combustion zone. And we also included an air staging. Now we're operating this boiler with primary and secondary air in order to have lower temperatures at the grate and to have a reducing atmosphere in the primary combustion zone and a turbulent secondary zone where we introduce the secondary air. And we applied a new approach for the control strategy. I will show that in detail on the next slide. Our new control is based on combustion calculation. It can adapt to the pellet quality, especially to the bulk density of the pellets, and it has optimized transients for a smooth modulation. And the last step, of course, was the testing after we did this retrofitting with the new EGR, the air staging, and this new control. So very briefly, what did we change in the control? Here you can see how the pellet boiler was controlled before we started changing anything. So we have a certain temperature of the water in the boiler, and the control unit says that means a certain modulation stage. And then it's quite simple. The pellet boiler knows a certain modulation stage means a certain speed of the pellet screw and a certain speed of the fan, of the ID fan. And like this, pellets and air are mixed together with some simple control loops, and that's basically it. And what we try to do now, we try to start with a combustion calculation. So it's still just the pellet screw and the ID fan, but we put in the pellets according to the thermal pellet input that we would like to introduce into the combustion chamber with the calibrated pellet screw. Have some thermocouples in order to adapt to the pellet quality. And then we do, in our control, some combustion calculation in order to insert as much air in order to get our optimized air-to-fuel ratio that we experimentally investigated before. Yes, and then we have some smooth transients in order to have a smooth modulation. So our test results show here in the case for carbon monoxide. When you take a look at the diagram, in orange you can see the CO emissions in ppm before we changed anything. So that was the basic pellet boiler, and you can see it's a typical graph for these emissions. We have quite low emissions at full load, but at part load these CO emissions increase. And what you can see compared to the blue curve, that we could significantly reduce the CO emissions in all power ranges. And yeah, you can see it has a minimum at around 10 kilowatt of thermal output. The reason for that is when you take a look at the part load, there the influence of the discontinuous fuel feeding is visible. And when we go to too high thermal outputs, then because of our exhaust gas recirculation, we don't have enough residence time in the hot combustion zone, and because of that, the CO emissions rise again. Similar diagram for our particulate matter emissions. You can again see in orange the emissions before our retrofitting, and in blue you can see we drastically reduced the PM emissions again. So now we have very low emissions of 2 milligram per 2 milligram per cube meter over a wide range of thermal output power. In order to get evidence why we reduced the particulate matter emissions that much, we analyzed our ashes with some samples from the standard pellet boiler and some samples after our retrofitting, and did some gave it to a laboratory in order to do some X-ray fluorescence analysis. And you can clearly see, especially in those big inorganic compounds in the ash, that we reduced. After our retrofitting, there is now more inorganic compounds remaining in the ash, so less inorganic compounds emitted as particulate matter. So that's a result of our reduced temperatures at the grate and our reducing atmosphere at the grate due to our primary measures. And one last time, this curve for our emissions. As we heard today previously, the NO emissions at solid fuels are mainly determined by fuel NOx. It has only a very slight influence what temperature we have inside the combustion chamber. But still, you can see in this diagram the influence of the temperature. When you take a look at this blue curve, that's after the retrofitting. And you can again see that we could decrease the emissions compared to this orange curve of the standard boiler by around 20 to 30%. And this is again due to the low temperatures and the reducing atmosphere in the primary combustion zone. The last result concerns the efficiency of the boiler. Here you can see two diagrams which basically show the same. So it shows the thermal efficiency of the pellet boiler over the thermal output. And when we started this lower diagram, you can see again, blue curve is our new efficiency. It's for a wide power range higher than this efficiency of the standard pellet boiler. But you can also see that it has a peak and then declines again. And the reason for that can be explained by the reason that we had previously. When you take a look here at the CO emissions, you can see a correlation between the efficiency and the CO emissions. And it's basically the same reasons that at hard load, we have this increasing air-to-fuel ratio that you can also see here in this diagram, which a higher air-to-fuel ratio leads to a higher exhaust gas loss. So more heat is brought to the chimney with the exhaust gas. So when we reduce the air-to-fuel ratio, we get higher efficiencies. And in the other direction, we have this insufficient residence time in the hot combustion zone. And that's why we have incomplete combustion and the efficiency declines again. So to give you a summary and outlook, as I said, the SolBioRef project, it started last year. Now we are currently in the development phase. So we already did this primary measures with EGR and air staging. And currently we are developing the internal heat exchanger in order to couple this biomass boiler with the ORC. And in May 21, so next year, we will bring all these SolBioRef components together in Nürnberg and in Athens and assemble 2 prototype systems of this soil bioref system, and then in the end do a 1-year field test in Nürnberg and in Athens in order to get evidence about the advantages of this soil bioref system. So thank you for your attention, and I'm looking forward to your questions.
Thank you, Maximilian, for the interesting presentation. Do we have questions from the audience? Peter, you have a question?
Yes, thank you. Very interesting presentation and impressive results, especially the emissions. Do you plan also to commercialize this technology besides this project? Because this would also be for normal stoves. Of course, very impressive emissions. You wouldn't need any particle filter and all these things. Are you planning this? And if you plan it, what is with the price compared to not to a OBI furnace, but to a good technology furnace, state of the art today?
Yeah, it's actually one of our project partners is this company you can see here in the middle, Ökofen, an Austrian pellet boiler manufacturer. They are within this project for bioref, and we got the pellet boiler from them. And they are currently about to save the patents for all that we did inside this boiler, and that's why I should not show too much of the results they said. But yeah, so they will commercialize the results probably in the near future. They told me something about October this year, so right now. And yeah, but they did not integrate our new control. I mean, they just integrated these primary measures, and I think that's quite well known that air staging and exhaust gas recirculation reduce the emissions. Yeah, but they did experiments themselves. They know the results from our experiments, and yeah, they adapted the geometry of their boilers so that they get these lower emissions. Yeah, so they are the ones who are about to commercialize the results. Yeah.
I also have a question. You always you look at 2 primary measures, which were exhaust gas recirculation and air staging.
Yeah.
Have you also looked at them separately, so you can differentiate the influence of each one of them?
Yeah. We first did include the air staging, and when we included the exhaust gas recirculation, we included a different kind of air staging. So we cannot directly say that was the influence of air staging and that was the influence of exhaust gas recirculation, because we did not clearly do that one alone first and that one alone second. It was a mix. We had a first attempt of an air staging, then we included the EGR with a different air staging. So it's a little mixed up, and we cannot say that's the influence of this and that.
So it comes as a package.
It comes as a package, rather.
Michael, you have a question. I think you're unmuted now.
Hello? Yeah. No. Okay. Just to clarify, this Öko-Ofen boiler has a nominal power of 9 kilowatts, and it had just a primary air injection, so there was no air staging in the basic model. So we didn't know that such boilers are still produced there. So air staging is already state of the art in every pellet boiler. So just wondering about that.
Yeah. This pellet boiler has a nominal power of 14 kilowatt, but it could operate up to 18 kilowatt. It's the same geometry. It's just a different software, so you can also use it with 18 kilowatt. And it has the standard boiler that you can buy commercially right now. Has no air staging. So, and it has quite good emission values even without our work before. It had quite low emissions of CO and particulate matter, so it was all within the regulations and far below the regulations. Yeah, and they managed to do it without air staging.
Yeah, that's very interesting to hear. Yeah. Okay. Thanks.
Maybe I can add. I don't know what Jürgen you think, but I think it's not state of the art at all. Especially at smaller pellet furnaces, often they have only one fan and just a flap. So nothing to control, and so air staging makes no sense if you don't control anything. And so I think it's not state of the art in this size of furnaces.
Okay, Jürgen disagrees. Okay, thank you again, Maximilian, for the nice presentation. Thank you for the question.